complexity and fraud, so related to the background, challenges, and actions. A little bit about myself. So I got my PhD a couple years ago in nutrition and food science, so at University of Maryland. And recently, I also got my MBA from the same school, and I'm a certified food scientist. And currently, I am a scientific liaison at the Chemicals Codex. So we develop high-impact standards on protein ingredients, spices, and colorants, and I coordinate the standard development lab projects. And I will talk more about the Chemicals Codex later. And currently, I am also managing I'm the managing liaison for the USP dietary protein expert panel. And besides work, I consider myself to be a good reader and a terrible equity analyst. So if you know, that means that, and in retrospect, that I probably shouldn't put University of Maryland in my MBA, after my MBA. So, and for today's topic, it's mostly about protein. So, what do you know about protein? And I guess that may be a little difficult to ask and answer questions. So I will just get the feedback from presenting the feedback from previous lectures. And there was one student saying that protein is complicated, and indeed that is true. So not sure how much you are into biochem or the general chemistry, but for amino acids, there are primary structure that consists of amino acids. The proteins consist of amino acids, so linked by peptide bonds, and there are secondary structure, and with two types, basically alpha helix and the pleated sheet, and there are 3D structure as well as multiple subunits forming a 4D structure. And so definitely that protein is complicated. And protein is also nutritious. And as you know that you probably have seen in at GNC or Amazon that there are so many different kinds of bodybuilding powders. They're all, the main ingredients are proteins. And we all know that for infant formulas, that the main ingredient there, or the most important ingredient there is protein. And so protein is definitely nutritious. And protein is expensive. So think about a gallon of vegetable oil versus a gallon or a big bottle of protein powder, and you can tell the price difference. And some people said protein is sexy, and I don't have that much love on protein. So unless that I am hungry for like 2 days, they will be probably sexy, but not that usually. So so the takeaway is that protein is very important. It's nutritious and it's complicated, and that's why we have this lecture. And so for today's agenda, we'll talk about the background, the challenges, and as well as the actions to fight against the challenges. And we'll talk about what FCC, the Chemicals Codex, has done on this. So a little bit about my organization. So Chemicals Codex, it was created by the US FDA and the US Institute of Medicine. It's currently published by US Pharmacopeia. It's a non-profit organization. So currently we have about 1250 food ingredient standards, and including additives, ingredients, and other food chemicals. The standards are created and voted by the expert volunteers, and we claim ourselves as the only fully independent source of food ingredient standards. So it's recognized by the US FDA and international regulatory bodies. So a bit about the structure of FCC. So in FCC standard, or we call it monograph, there are the following sections. So there is the description, the chemical information, the identification, and assay, which is the purity of the ingredient, as well as the impurities, and such as the heavy metals and pesticides. And there are also specific tests to strengthen the understanding and the characterization of the ingredient. And so today we'll talk about food fraud, or some people mention it as economically motivated adulteration, so EMA. And in our FCC, there is the definition here. And you need to take a look at it very carefully because some people are really confused about the definition. And it means the fraudulent addition of non-authentic substances, or the removal or replacement of authentic substances without the purchaser's knowledge for money, for profit. So in here, we talk about an example, which is milk. So we talk about dairy ingredients adulterations. So as you can tell that in the past 10 years, there is quite a significant number of adulterations, especially in the early 2010s. And in the recent 2 or 3 years, it seems there is a drop on the trend, but still 27 or 39, they are significant numbers. And interestingly enough, I usually ask the question, and for this setting, I think it's kind of difficult. And not many people realize that the most popular adulterant is actually water. And surprisingly or non-surprisingly, it's easy to add. So if you are selling milk, if you are adding 10% of water, then you get 10% of your revenue. So sometimes that relates to more than 20% of profit. And we can also tell from this figure that it's a long tail effect. Although water or urea, those are the two most popular adulterants. And when you look at the whole picture, there's definitely a long tail effect, meaning that there are all sorts of different adulterants found in milk. So related to our testing strategy, I will mention later that only testing 1 or 2 compounds in milk testing is not enough, and we'll talk about that later. And when you take a look at the history, and sometimes it can tell you the future, and it dated back to 1850s, and in the US, there is a scandal called swill milk scandal. So the cows were actually fed with swill, which was the residue mesh from the distilleries. And the milk was whitened with the plaster of Paris, thickened with starch and eggs, and fumed with molasses. So it is said that there were 8,000 babies with that. And the most known one is probably the melamine incident in China. That's probably about 10 years ago. So melamine was actually a chemical that is really high in nitrogen, and it's not a food product. It's not a food ingredient. So it was illegally added into milk to artificially boost up the apparent protein content. So there was, it said that there were 300,000 babies were sickened. And to this day, in China, most of the parents still do not trust the domestic supply chain of infant formula. So they buy a lot of overseas infant formulas. So the effect is definitely significant. And in 2013, and in Brazil, there is a incident called compensated milk. So there are about 100 million liters of milk, and there is an estimate of 1 million pounds of formaldehyde containing urea was added. And very recently, a couple months ago in India, so there is a synthetic milk incident. So this is not the artificial milk that so high tech or something. It's really the factories are manufactured synthetic milk by adding chemicals such as the sodium sulfate, caustic soda, chloroform, palm oil, hydrogen peroxide, maltodextrins, and shampoo, etc. So there were many people were arrested in this incident, but the causality is still unknown. So I guess that we talk about from the criminal side, how do we make profit? And when you take a look at the adulterants found in milk, apparently they can be separated into different categories. For example, melamine and urea. So those are nitrogen-rich compounds that to boost up the nutrient testing results, and vegetable oils, and it's used to improve the texture, increase the nutrients, and increase the mass and density, as well as to add the flavor, because oil makes you make things tasty. And so maltodextrin starch, those are used to boost up the texture and increase the density, increase the flavor, similar as sugars. And detergent is used to improve the texture. And so you get the idea. And for today's lecture, we focus on why people are adding melamine or urea and how do we deal with those. So let's take a step back on how do we determine the protein content. So it is kind of a history of battles. So there are two analytical approaches. Approach one is direct gravimetric measurement. So basically, you isolate your protein from your food and just take the weight to measure the weight of that protein. And approach two will be indirect approach. So because it seems like the approach one is too complicated, and people think, well, total nitrogen is actually correlated to the content of protein. So measuring total nitrogen content of food, there is no separation step. So we can just use a conversion factor. So times, for example, times 6.25 from the total nitrogen value, and then you can get a total protein. So in brief, that approach one loses the battle. USDA said that, well, the quantity of the protein in material is not easily separated and weighted, as done in fat and other food constituents. And so instead, the percent of protein in the material is calculated from the quantity of nitrogen it contains. So basically, people say, well, let's do nitrogen. And so for nitrogen, there are basically two people are doing that. So in 1800s, there are people finding that a protein definitely has about 15.7 or 16% of nitrogen azote. That's what they call it at that time. And so people think, oh, there is a correlation. And later that they found that, well, actually in a lot of fertilizer, they consider nitrogen as part of the nutrients, which is true for plants, but not much for humans. And later that there were two great guys. One is called, the last name is Dumas, the other is Caldo. And some people like them, some people hate them, because Caldo is really a tedious chemical approach to determine nitrogen, but still it's a golden method. So people use it all the time, and some chemists are not happy with that. And so over 120 years later, that nitrogen basis method is still the reference method. And so this is the basics about Caldo. And basically, when you look at the formula, it seems complicated, but it's not that complicated. And basically, you digest the sample and to make it as the ammonium, and then you capture the ammonium with the borate OH3, and then you back titration with a base. So that's the principle. And for tumors, it's a different approach. Basically, you burn it, you combustion with a 900 Celsius chamber, and so the nitrogen in the protein converts to a gas, a nitrogen gas, and then it passes through a special column that can separate out the carbon dioxide and water. And then there is a detector at the end to use measure the nitrogen content. So this takes about 2 minutes, and it's much faster. And I guess that people have more luck on tumors than Caldo. So the pros and cons. So the Caldo used for 100 years, there's a reason behind it, because it's very precise, meaning that everyone is, if you are a student and you do the experiment for 5 times, almost that you get exactly the same results. And even for students A and student B and student C, when they do the same samples, they almost get a very, very close result. So the precision is pretty good. And the negative point, the cons, is that the selectivity or the specificity is not very good. Ideally, they should only determine nitrogen only from the peptide bound amino acid. But Caldo actually measures nitrogen from any source. So anything with the nitrogen element, basically it can be accounted. So what's the problem? So it seems like it's a simplified method, and what's wrong with it? So that's the cons of the total nitrogen method. Criminals know that the nitrogen method has measured for every single nitrogen. So they deliberately added some nitrogen-rich chemicals into a protein ingredient to boost up its nutrition value, so they can sell at a higher price. So the compound here is, the substance here is melamine. So melamine is actually toxic to humans and pets as well. So in 2007, there were thousands of pets died from adulteration of melamine into pet foods. And in 2008, there were many babies sickened because criminals added the melamine into milk, and the milk made into infant formula. Infant formula will feed it to infants, and a lot of babies were sickened in China. And as I said, to this day, that the Chinese parents still don't trust the supply chain of the Chinese milk products. So that caused a lot of issues. So as said, that melamine is just one kind of chemical, and they can add all sorts of different nitrogen-rich chemicals as long as they have a higher nitrogen content than normal protein. So there are many, many options they can choose. And there is a secondary method for total nitrogen, which is near-infrared method. So we know, you probably will know, that the near-infrared is basically overtones of molecular vibrations. So a lot of the substances or chemicals have vibrations in different wavelengths. So in that case, that you can measure the signal and then tell how much chemical you have. So the near-infrared does not sense nitrogen, but it sends the NH vibration of the amino acid to as an indirect way to sense protein. So there are common bands at 2055 to 2100 and 2180. Those are common for use for proteins. So it's usually a secondary method, means that it will be calibrated against the primary method, which are the Caldo or Dumas method. And so the problem with near infrared is that it's very similar. So it's not specific enough. So in 1980s, urea was added to wheat to artificially increase the nitrogen content. So that increased the protein content in the measurement. So it happens in Minnesota. So urea was added because it has higher nitrogen content than protein, and it can be falsely measured by the golden method, the Caldo-Dumas, as well as near-infrared. So why urea can be measured as protein is because, as I said, that for commonly used bands for protein measurement are 2055, 2100, and 2180. Urea has very similar bands as those wavelengths. So in that case, that they can actually boost up the protein content in your wheat or wheat proteins. So from a criminal standpoint, that we calculate how much they can earn if they are falsify the protein. So there is two types of wheat. So it's a premium wheat, which contains 12% of protein, and there is regular wheat that contains 11.5% of protein. So the premium ones sell for a premium. So here is the recipe for adding just 0.06% of urea. So in that case, that the cost of the fake premium wheat is $12.02 per bushel. And actually, you can get a profit of 1.1 per bushel and almost 900 for a truckload. So pretty sweet, right? Unless that some people may find it, and then you go into jail. So in short, that the common protein testing includes the Caldo, Dumas, and near-infrared methods. So they are not necessarily testing the proteins in the food matrix, let alone the right proteins. And the criminals know that. So what are the challenges here is that, well, we don't have sufficient analytical testing. So first, that the Caldo, Dumas, or near-infrared, they are not sophisticated enough. And also, people are not doing enough testing for every batch of your samples. And also, as people always say, so transparency is very important. So a lot of time, lack of supply chain control can cause you a problem or a jail time. And here are the actions that that we can do. So there are two strategies. One is that we can target the adulterants. For example, we can look at the nitrogen rich compounds. So we look at the melamine, test that if it's there. We look at urea, and we can look at the added carbohydrates, including the starch or the sugars, and those are sophisticated methods out there. And we can look at added fats. We can we can look at the proteins and whether they're the right proteins or whether there are other proteins added. And we can look at whether they have preservatives added unauthorized. And however, as I said, that well, there are many choices that the criminals can use. Basically, as I said, there is a long tail effect. You can use any of those nitrogen-rich compounds to add into your milk, and then you can falsify it as a higher quality milk or a higher protein ingredient. And criminals can design adulterants to evade the existing QA system. And the QA system reacts by developing new tests. So today you are using melamine. Okay, QA system, quality assurance system can detect melamine by developing new methods. And then some people use urea, some people use other nitrogen-rich compounds, and the QA will just basically doing a pursuit of those. So this is kind of an endless circle. And what is the solution here? And this is something very new in the industry, is that instead of looking at the targeted analysis, instead of looking at the adulterants, we can take a look at the authentic signals. So let's focus on the milk, or the focus on the protein ingredient itself. And let's look at what the authentic signals should look like if it's a normal milk from mammal and produced, say, in winter, in November, in Maryland. So what should that look like? So based on that strategy, that we have two things to look at. One is that we can focus on the specification. So in FCC, in our publication, we have specification for ingredients. So for example, for whey protein, we will include the test for lactose, nitrogen, non-protein nitrogen, fat, and moisture, ash, and pH. So so all those tests will have a specific range. So if your ingredient is falling out of that range, it means that, well, something fishy is going on. Either it's not a good quality one, or maybe someone added something or replaced something with it. And the other approach is that we can use a modeling approach. So basically, it's a fancy term of statistics. So we can use so-called chemometrics and to focus on modeling the authentic signals from different techniques. So not sure if you have been through the chemistry class or the general chemical analysis class, but then there are near-infrared spectrum, mid-infrared spectrum, Raman spectrum, liquid chromatography, gas chromatography, NMR, and Methoc, etc. So there are all sorts of methods that we can use to model the authentic signals. And so in order to do those, there are a few questions that we need to ask ourselves. So one question is, say, is this triangle different from the other, say, the rectangle? And so basically, is this milk different from the other milk? Or so from here, you can know that, well, the triangle is definitely different from the rectangles. But in reality, it's something like this. So we have a triangle, but the other milk doesn't look like just a rectangle. They can look like a very different type of shape. So that makes your judgment very difficult. So is triangle different from those other shapes? And so the reason behind this is because for milk, it's a natural product. So it's not just like, well, you always have, say, the chemical synthesized one that you have 99 purity, you have less than 1% of moisture. For milk, so different places, they produce different milk. And for different seasons or with different speeds, they will have a different composition. And so the same applies to other protein ingredients. So you have the variance from your own material. So that makes the testing, the comparison kind of difficult. So what we do is that we need to model those differences within the species. And so to see how significant that your tested material is different from the library of your current materials. And one example here is that we can test for amino acids. So amino acids are the building blocks of proteins. and we can measure each individual amino acid and tell if the fingerprints match the materials. So the testing method is we use microwave hydrolysis or oven digestion to digest the protein into amino acids, and we'll get the fingerprints of that based on the UHPLC, which is one type of liquid chromatography, and we'll compare that to the authentic fingerprints of the materials. And in that case, that we can compare it to other foreign proteins as well. So if that match, then if there is a mixture of different types of protein, we'll be able to know. So here is a very brief demonstration of the amino acid fingerprinting method. So for example, for the baseline, basically that's the level of the skim milk powder, which is one important commodity for milk. And for wheat, for pea, for rice, for soy, they're represented as different colors, and that the bars represent the deviation from the SMP as percent of amino acids. So we can tell that for wheat protein, if they had a higher glutamic acid, then it means that, well, it's actually, you can tell from skim milk powder. And for others, it applies same principle. And on the other hand, that for skim milk powder, for various different types of skim milk powder from 3 countries, 10 production locations, different processing conditions, they get a very, very consistent result for different amino acids. So that's basically a good news that, well, the intra-species variation is small, and for different proteins, it has very different amino acid profiles. So basically, amino acid is a very successful or useful way to differentiate between proteins. And so as we test it, we can tell that if we add 5 or as low as 1 or 2% of foreign protein into a skim milk powder or a milk protein, we will be able to detect that. So that's a very good performance. And there are other techniques such as using a whole protein, intact protein technique using gel electrophoresis, size exclusion, whole protein Methoc, or the MODI-TOF. And there are other techniques that can test for basically everything in that protein ingredient. So for example, for NMR, for near-infrared, for FTIR. So those are useful in this manner. So for my summary, so protein adulteration and fraud are real threats to stakeholders and to you and to us. And there are common methodologies, but they are not sophisticated enough. Testing, both including the targeted and non-targeted ways, are critical. And for Food Chemicals Codex and our related work have got against the economically motivated adulteration, and through the targeted adulteration detection methods, and as well as ingredient specification, as well as the non-targeted methods and guidance. So hopefully that you get an idea about what adulteration is and what the threats and how we can deal with it. And that will be all for my presentation. And if you have more questions, not sure if the technique and time allows that you ask questions, but my number and my email is here. So I think this is also recorded, so you can take a look afterwards. Thank you. And Brandon, what's next?
Yeah, so I did record it, and then Dr. O'Keefe is going to send that out to everyone that wasn't here and stuff. And then he provided his email, so if you have any questions about anything, it was pretty interesting stuff. And then I think that'll be it.
Sounds good. All right. Oh, thank you, everyone.